Once again, everybody always this very fine interview.
So this is the second half of our interview, and we shall start off from question number 6 up to question 8. So sit back, relax, and enjoy. Question 6, concerning the limits on the anagram distance measure.
ADM is a real positive number, but does it really mean it can grow indefinitely towards infinity, even for finite sequences, or might there be a finite upper limit for ADM that's perhaps a function of the cardinalities of the two sequences involved? We see you've managed to define absolute limits, even finite ones, on the bounds of all the 4 basic arithmetical operations with your GT&C theory. Might you have similar theories on the limits applicable to the anagram distance measure?
Yeah, wow, thanks so much. You are really my favorite students, and thanks for bringing this up. So yes, the anagram distance measure, ADM, is indeed a real positive number, which would mean that it can range, from 0 to positive infinity. But you're also right, and it's right to be concerned as to whether, it has no finite upper limit other than just infinity, So first of all, realize that, the ADM is a measure that is only well defined for 2 sequences that at minimum have exactly the same length and which contain the same distribution of elements, even though their relative ordering in either sequence might be different. So we shall for now only be concerned with such legitimate scenarios only, want to only look at analyzing anagrams and what are sometimes known as permutations. High school mathematics, for example, pure mathematics, looks at permutations and not anagrams. So this anagram distance measure cannot fall below 0, and this is guaranteed by the fact that in cases where any 2 sequences of the same length differ by a difference in at least 2 positions. And I stress 2 here because if you started out with a sequence such as TWO, which spells out the word 2, and then try to shift any of its letters to a new position, then at minimum you must end up shifting at least 2 elements. There is no way to move the letter T, for example, to a new position without also shifting another letter. So similarly for the other letters, W and O in that word. So thus, most of our basic anagram transform, may be a mere swap of at least 2 neighboring letters, such as when we swap W and O, so that we end up with a resultant sequence T-O-W, which spells out the word tow. That means, pulling something, towing. So in this case, you see that the first letter wasn't shifted, the T remained in its place. So in the ADM formula, that would result in a value 1 minus 1, which is 0. And in case we hadn't shifted any of the other letters from their original positions to, then the entire numerator part of the ADM ratio would result in 0. And so that, irrespective of the size of the sequence, the ADM would be 0 in cases where the transform results in no change of the position or location of any of the original sequence elements. So 0 is our lower limit for this reason. However, and such as in the case of 2 and tow, we find that we have some noticeable differences in the letter positions when we compute the location update. So in this case, for example, we see that processing the letters left to right, we have updates such as 1 minus 1, 2 minus 3, and 3 minus 2, and this would result in 0, -1 and +1. And so if we just sum them up without computing the absolutes, this would give us something like 0 minus 1 plus 1. Of course, this would result in 0, and it might seem like we are saying that the phrase or the word TWO and TOW are the same, which is absurd. So no, in ADM we compute the sum of the absolute differences. We have to square and then take the square root of the differences. So that then in our example case here with 2 and tau, we have 0 plus 1 plus 1, which is 2 as our numerator. So that's the numerator is always guaranteed. It will always be a positive integer, and it will be a whole number. That is in the language of GTNC theory. So on the other hand, the denominator is just the cardinality of the input sequence, and this wouldn't matter even if we looked at the cardinality of the resultant sequence, because ADM deals with anagrams, and as we have seen, anagrams of the same sequence will have the same length. So moreover, the ADM can't be applied to a case where one of the sequences is of 0 length, because that wouldn't make sense. You can't have an anagram of the empty set, or even if it were, there would be no change. So computing the ADM may not make sense, or it will just be 0 anyway, by convention. So we know that the denominator in the ADM shall always also be a positive pure number, since there is no sequence that can have negative number of items. So essentially, there is no negative counting number that we're going to come across. It's either 0 or 1 or plus. So that's taken together. The ADM is a ratio of a positive whole number to a positive whole number, and such that the denominator is guaranteed to always be greater or equal to 1. So this then makes the ADM take on values from 0 to positive infinity, since we know that there are legitimate cases when a fraction may result in a numerator that's greater than the denominator, and that's possible even with the ADM. However, that is just the preliminary analysis. Anything further than that is exactly where we might want to put everything else aside, and scrutinize the matter deeply. Yes, put on our punching gloves and our security glasses and helmets and get in, or if it's swimming, put on our aquatic gear and go to the deep end. So that's the stuff of real analysis, and since you're a student of advanced calculus, perhaps it explains why you're interested in that. So it surely does make sense, and we shall not really want to go into that, though we've done something similar for addition, subtraction, multiplication, and division when we developed GTNC in 2020. However, you brought this up in an interview, and this is it's still 4th of February right now, and the lecture was just given a day before, and we have not yet even finished breakfast here. And we have a birthday on our hands, so please first leave that for now. We shall come back to it, and we need to go and catch up with these guys, eat some cake, and maybe we'll figure it out as we slice the cake amongst a finite number of attendants. So hopefully we shall settle that matter. So that's it. Look forward to it in a future paper or in a book. We shall definitely get to handle that, and perhaps I hope you can come and join us as we figure it out, yes, on this great day, taking some cake and having some tea.
Question 7 concerns cases where ADM is applied to sequences of unequal lengths.
Also, osobola okutegeera oba batabuddwa bulungi nga weeyambisa eno anagram distance singa entuula yaabwe kale ekyukakyuka buli luvannyuma lw'ekibuuzo ekimu oba nedda.
What happens if you have to compute the ADM for two sequences that aren't the same length? Such as if we have to form 2 or 3 columns of 19 students in an exam room, such that their relative seating order changes after every exam, and so they don't have a chance to copy each other, like when two friends, always sit next to each other in 2 or more exams. Is it feasible? Because it looks like the ADM formula wouldn't be able to handle such cases. Yes, alright, this one is also funny, but yes, we could use the ADM to analyze the ordering of student seat allocation in an examination room. If we had several sessions and we want to prevent having the same relative ordering across 2 or more exam sessions, However, some careful modeling would be necessary, to make this kind of problem tractable using just the ADM. For starters, you have to note that if we model our classroom, as a Cartesian grid or matrix of say 3 by 4, meaning it would sit at most, 12 students instead of the 19 that the reviewer, is talking about in their question. This simplification shall make sense because, as with many kinds of problems we encounter in mathematics, many times can solve a hard problem by first solving a simpler version of it. So, assuming we have this room in which we form 3 columns of seats and that we wish to ensure we can detect if any 2 students are sitting close to each other across more than 1 exam, it is important that we know that there are several multiple ways in which we can analyze this, and some analysis methods might be more complicated or difficult to model than others. For example, if we encounter a scenario, and this is really somewhat complex, where we wish to ensure that no 2 students sit next to each other across any 2 exams, and yet our meaning of closeness or proximity takes into consideration, one's immediate neighbors in the same column, but also in the same row, and also immediate neighbors, by diagonal orientation, So essentially meaning everyone within a circle, around one seat, whether you are in the left, the right, in front, behind, but also diagonally close, that all those, count as neighbors. So you find that we are looking at, let's say, a radius of 1 seat from the person. So this situation or model may be tricky to solve, but even though we could use an anagram distance for it, however, it may not be the kind that we want to give to beginners, and this lecture was about beginners. It's not for professors or PhD mathematics students. So this analysis scenario should be avoided, and maybe we keep that for a later time. Then, and so if we were to approach this with a somewhat simpler model, you might know that, for example, that if we ignore the fact that we form 2 or 3 columns, which is like dealing with a higher order sequence such as a matrix, and instead focus on reducing the ordering to just a long flat sequence that merely wraps around problems and theory that you find we have covered when dealing with transformatics and genetics, for example, like when dealing with sequences of n-grams. Then we can merely treat of all the members in the exam room as elements in one flat sequence of maybe 1 times 19 seats, or as in this case here, after we have simplified it from a 3 by 4 model, it would become a 1 times 12 sequence, perhaps a vector, or in computer science terms, just a list. So with this approach then, using a flat sequence, it wouldn't even matter how many rows or columns we form in the room, literally. All that matters is that we can enumerate the seats 1 by 1 in some consistent order, from the first to the last, to specify or give us the ordering of the seats in the sequence. So we might, for example, count down the first, then leftmost column, then up the next column, and then down the next, etc., to form the sequence. And with that kind of approach, we would find that the most important factor is that we need to follow the same direction of counting and enumerating when looking at different sessions. Like if in the first exam we counted from the leftmost column and to the rightmost, in the second exam we want to follow that same ordering if we want to still arrive at a sequence, a flat sequence that will help us to solve the problem. And also we want to make sure that all the first n seats are occupied, even though the ordering of the students may be modified across the sessions. So if we do that, then we can merely compute the ADM between any two given seating arrangements, as long as the students attending the exam are also the same, and that no two students or more occupy the same seat at the same time. Even if they are twins, please put them on different seats. Yes, Olga and Maurice, they like to sit next to each other all the time. No, please, you have to put everyone on their own seat, and that's it. So we shall be able to discover that. So this can help us to determine whether we have kept students seated in similar positions for too long, if we use the ADM, that is, and that flat sequence model. And it can help us to avoid things like stagnation and other intellectual problems in the class community. Yes, who knows, it could even be applied in normal sessions, not only in exams. So concerning how we would leverage the ADM results, it would be noteworthy to know that the larger the ADM between any two pair of seating arrangements, the better. So that means that if in exam 1 versus exam 2 we got an ADM value of 0.66, and yet in exam 1 versus exam 3 we get a value of 1.414, then it means that the difference between the seating in exam 1 when compared to that in exam 3 was more randomized. So the larger the anagram distance measure value, the better, or the clearer it becomes that we have randomized or shuffled these positions better. So however, in either case, there might exist seats that are left blank. Maybe the first two seats are occupied but the third is not, and etc. Or that you find that you have introduced some students that were not there in previous sessions, etc. So these can complicate our using of the standard ADM formula, and so you want to take care of those problems. Then the other tricky case, of course, is when you have students that have to leave. They have to leave the exam. Maybe they do paper 1 but they don't do paper 2, etc. Or maybe you're keeping 10 students per room, but some of the students from room 1 are shifted to room 2, and those in room 2 are shifted to room 1. Still they are 10, but they have changed, so we may not readily be able to use ADM because the elements in ADM must be similar across the two sequences we are analyzing, even if their positions have changed. So those are some of the corner cases you want to worry about, and otherwise in all such cases you just need to be creative and be a thoughtful mathematician. You'll still find a way to use the ADM or the anagram distance idea, but with alternative formulations, and your formulations may not look anything like what we have put down in our literature, because what's most important here is the idea. So how it is applied can many times be adapted to suit the problem or the case, or we can somehow we don't break Newton's laws of mechanics every time we solve a different kind of mechanics problem, but we can bend them or restructure or rephrase them or something like that. So the same with ADM here. So that's it. And when we're dealing with other kind of sequences, not necessarily seats of students in a room, like DNA sequences, we can still apply it there. And we see that mathematics is actually mathematics. If the formula for the anagram distance measure has worked in one particular scenario where we have two two sequences and it has worked well, and we have two other sequences but maybe of different objects or different kinds of variables, still it's mathematics, it will work. So that's it. So the theory can always be adapted to new problems, or it can be, you can find that the problem can be slightly modified so that it fits the theory that we have, and that should work. So that's about it.
Question 8 concerns other sequence analysis measures in Transformatics.
Aitiwe mukama manyao usobuzi ufoka abara kwenda twegise emiringo yona yokwita maraka ebitekerezo omabale ekalira mukweto ekusoka tukegereza ADM kurungi ariko akutekwa kuba hariyo namagesigaadi gatayina rangi za Transformatics mutuyambe mutwegese philosophy zinu empya.
But we have liked this mathematical elucidation so much and have picked up lots of insights concerning what this anagram distance measure and transformatics is all about. However, what are the other ways in transformatics by which we might quantify the difference or similarities between sequences, or for analyzing items in some sequence? Please educate us more concerning this.
Yes, thanks for being attentive and picking, something or more from all this discussion. So sure, Transformatics is bigger than just anagram distance theory. In fact, if you look at the Transformatics one-on-one thesis, which lists 10 foundational results for the field, as well as 10 foundational proposed applications of its core theory, you find that the anagram distance measure is just one of the 10 proposed domains for applying this new mathematics. So in the thesis, it's just proposal number 2. And concerning other methods and theories relating to how to quantify the similarities or differences between sequences, note that the Transformatics thesis also lists and introduces, but also discusses other ideas such as the TCR, which is the transformer compression ratio, and it treats of cases where you care less. This one here treats of cases where you care less about the composition or relative ordering of members in any two sequences involved in a transformation, but only care about whether the cardinalities of the sequences change or not, and if they change, by how much. So it results in a real positive number that can tell us whether a transformation resulted in a protraction, such as when by adding yeast to your baking dough results in a bread, chapati or mandazi that occupies a larger volume than without. And also if a transformation resulted in a compression, such as when ultra freezing of a gas results in a liquid that generally occupies less volume than the original gaseous form of the matter, TCR would be able to express or capture such transformation properties. And then we have proposal 4, which presents the piecemeal compression ratio. So this one also helps in quantifying changes in sizes across transformations. However, unlike the TCR, for which it looks deeper into the composition of the two sequences which are involved, and especially focuses on the relative composition of the common subset of elements in either sequence before and after the transformation. So it likewise results in a real number. However, unlike the anagram distance measure and TCR, the PCR can be negative. So TCR and ADM are always positive. They can be fractional, but they're always positive. But PCR can be fractional, can be a whole number, but it can also be negative. So that is one of its properties. Now, if you look at the literature, you will see why, based on how it is defined. And then, especially when we wish to analyze two sequences of possibly different length, but which still share a similar symbol set, we also have another measure known as the model sequence statistic, MSS. So that can be very useful in building solutions that compare a sequence to a collection of other sequences, or in problems such as we find in artificial intelligence, in machine learning, such as in classification, in clustering, in logic, leveraging learned decision surfaces, etc. So model sequence statistic is very useful in such cases. Statistical artificial intelligence, yes, those kind of things. Then you notice that there is a whole other body of results and theories in transformatics that we could use to apply to comparing two or more sequences at once, or if we only want to analyze a single sequence, and nothing else. So some of these other results or theories, for example, are like what is possible using what we call higher order sequence transformers. Higher order sequence transformers, are such as, for example, T programs, and you find that these can be used to almost create any kind of transform. You can even transform a sequence to a metric, or to a KPI, or to a statistic. So all those other measures we've looked at could be implemented using a T program, for example. So these higher order sequence transformers are that powerful and general. And then for very special cases, one might wish to compute a single number that somewhat describes or summarizes any kind of sequence, irrespective of the kind of elements it contains or what it's being used for, in the most abstract or philosophical way. So in such case, Transformatics has proposed a new measure, and somewhat in the spirit of Claude Shannon, Claude Shannon, 20th century mathematician that did a lot of analysis around information theory and groundwork. So it gives us, Transformatics gives us a new measure for information in any arbitrary message, but this time when the focus is on the form of sequences, and it's called the sequence entropy measure. So overall, yeah, Transformatics, despite being a very young field of mathematics, and that most of the work and theory it presents has been, developed, applied, and reported by a single researcher, myself, future Professor Joseph Ulrich Lutalo, at Nutri's Research. I always wake up in the morning, look at myself in the mirror, and think of all the things I've done, and surely I say, yes, I am Professor Joseph Ulrich Lutalo, and despite universities out there not wanting to recognize my work or recognize me, or no one wants to call me professor, but in my heart I know I am, because I've really earned and done the work that I trust and believe professors do. So yes, as time goes on and as more people become more familiar with these ideas, the theory and applications, such as this new computer programming language, T, the Transforming Executable Alphabet, based on Transformatics, then I trust that the wider body, a wider body of knowledge, theories, and applications leveraging and extending Transformatics shall grow, and perhaps transform into a compelling mathematical machine or mechanics, that people can readily leverage to simplify or solve difficult problems, not just in today's world or this year or tomorrow, but for a long time to come, for centuries or millennia. And I trust that both the theory and practice of this beautiful language, universal language that we call mathematics, shall surely benefit from all that we are doing with Transformatics. So that's about it, and hopefully, yes, all your answers, all your qualms, all your concerns are now resolved and settled.
Thanks for listening and being part of this wonderful interview. Cheers and have a nice time. Till we meet again.